Hi, this is John Whitaker for the Mathematical Analysis class, and this is our 9th lecture. And we were just starting to talk about integration, in particular the Riemann integrals what we're working with. And the name of the chapter 6 was Riemann-Stieltjes integral, and it's a little bit more generalization of an integral. And let us review something we wrote last time. So here's what we did with last time. In a definition, is we said that we let F be defined from the closed interval from A to B into R, so it's a real value function. B, a bounded function. And then what we said was we define, so here's the first part of this definition, we define the upper Riemann integral as, so we have from A to B with a superscript bar here of f dx to be equal to the infimum over all partitions of the upper sums with a partition of that. And 2, we define the lower Riemann integral as, okay, so we integrate from A to B, we have a subscript bar here, lower, of f dx, and that's going to be equal to the supremum over all possible partitions of A to B of the lower sums with respect to the partition in F. So that's what we had left off with before. And then where the supremum over P and the infimum over all P are taken, as I said, over all possible partitions of A to B. Now, the next thing we'll do is, that's a review. The next thing we'll do is make another definition. It says, let F be defined from A to B into R be a bounded function. And we suppose that this upper Riemann integral equals to the lower Riemann integral. Okay. Then we say F is Riemann integrable on A to B, and write, to denote this, we write F is an element of this fancy R, meaning that F is a Riemann integrable function, and the Riemann integral from A to B of f dx is going to be equal to the upper Riemann sum from A to B which of course is the same thing as the lower Riemann sum. Okay. Now, first thing I think we should observe is that, note, for each partition, script P of the closed interval from A to B, and F going from A to B into R being a bounded function. We have that B minus A times M, where we think of this little m as the infimum of all output values for F on A to B, that's going to be less than or equal to the lower Riemann integral with respect to P and F, which is going to be less than or equal to the upper Riemann integral with respect to P and F, which is going to be less than or equal to big M times B minus A. And that big M is the supremum of all output values of F on the interval from A to B. And so, when we think of the set of all numerical values for the lower Riemann sums, and the set of all the numerical values for the upper, and I shouldn't have said Riemann sums, I should have said Riemann intervals, upper Riemann intervals. Okay? These are bounded. Bounded sets. Okay. Thus, the supremum over all possible partitions of L, the lower Riemann integrals, exists, and the infimum of all possible partitions of A to B of the upper Riemann integrals exists. So that integral with the superscript bar, that always exists, and the integral with the subscript bar, that always exists. But they aren't necessarily always equal to each other. And so let's do an example here where we do have a Riemann integral function. I believe the simplest example of a Riemann integral function is a constant function. So here's a fact. It says if F defined on A to B into R is given by
f of x equal to c, then the integral of f of x dx from a to d, Riemann integral, is equal to c times quantity d minus a. And so that makes be a Riemann integrable function on a to d. Let's do the proof of that. Okay, so here, if you let strip P be any partition of A to D, then the let's start off with the upper sum, the upper Riemann integral of this partition with F. Well, its definition was that we're taking the sum of these maximum values of the function, I shouldn't say maximum, supremum values of the functions over these subintervals from x sub I minus 1 to x sub I, and then times the distance of those subintervals, which we call x sub I star here. And so what this is going to be equal to, that supremum is always the same. The supremum of this function, since it's a constant, is always c. So this is equal to the sum, as I runs from 1 to n, of c, and then it would be times this distance, x sub I minus x sub I minus 1. This is as I runs from 1 to n. If we expand that, that's going to be equal to c times x sub 1 minus x sub 0 plus c times x sub 2 minus x sub 1 plus c times, well, we continue on in this way until we get to c times x sub n minus x sub n minus 1. And if we were to multiply this out, a lot of the, almost all the terms would cancel with each other. For instance, c times x sub 1 here, and then we have a minus c times x sub 1 here, and they would cancel. What we'd be left with is a c times x sub n minus a c times x sub 0. But x sub n, for being a partition, being the last value in a partition, that's equal to b. So this is c times b minus, and the first number in the partition is a. So c times a, and so that's c times b minus a. Okay? So that's what the upper is, the upper Riemann integral for any partition we have. It's always that. Also, for the lower Riemann integral, we're going to get exactly the same thing in that we're going to have this sum as I runs from 1 to n of the infimum value over the subintervals, delta xi. And what that's going to be equal to is exactly the same thing, is c times b minus a. Okay. And so what we get is that the supremum over all partitions of the lower Riemann integrals, well, that's this is always just one number, and that supremum is just going to be c times b minus a, and the infimum over all partitions of the upper Riemann integral with respect to any partition in F, that's going to be equal to c times b minus a. So they're the same values. So that means that the Riemann integral exists and is equal to this common value. And that's c times b minus a. Okay,
We're using these infimums and supremums, and I'd like to go back to their definitions before we go any further. And let me have us recall that if you let E be some subset of R, which is bounded. Well, in this case, we'll just say bounded above. Okay? And suppose there exists an alpha that's a real number, such that two things are satisfied. One is that alpha is an upper bound for E. What that means is that for every E element of big E, we have the E is less than or equal to alpha. And two, if gamma is less than alpha, then gamma is not an upper bound of E. Then alpha is the supremum of E. Okay, that is alpha equals to the sup of E when we write it. That's its definition. Okay. Well, similarly, we have the definition for a theme, and let me write it up. Let's recall, if we let E be a subset of R, be bounded below, then suppose there exists a beta element of R that satisfies two things. First of all, beta is a lower bound for E. Again, it means that beta is less than or equal to E for all little e's element of big E. Two, if beta is less than or equal to, is less than, I should say, some gamma, so we got gamma bigger than beta, then gamma is not a lower bound of E. Then beta is the infimum of E. That is, we say beta equals to the nth of E. Okay. As a fact,
and this is the fact we use in the proof, it says if E is a subset of R and S is a subset of R, and we're going to say both of which are bounded. Bounded, and I'm going to say non-empty sets. And then we have we have one more restriction. With, we'll say that E is less than or equal to S for all E element of big E and S, little s, element of big S. Then, turns out that the supremum of E has to be less than or equal to the infimum of script S. So that's a fact. And as I said, that's something we're going to use a little later on in proof. Okay, we've got a series of definitions coming up. Really, these definitions I'm about to list are an extension of the Riemann integral. And that has to do with what's known as the Riemann-Stieltjes integral. Here's what it says. It says, let alpha be a monotonically increasing function on A to B. And having that being said, it follows that alpha is bounded on that integral from A to B, that closed interval from A to B. Then corresponding to each corresponding to each partition of A to B, we write, so here's some definitions. We write down first the delta of alpha is equal to alpha x sub I minus alpha acting on x sub I minus 1. Okay? And then, for any bounded function f acting from A to B into R, we define, okay, so this U P, with respect to P, F, and alpha, is going to be equal to the sum, as I runs from 1 to n, of the big M sub I times the delta alpha sub i's. So that's the first definition. Second definition is we have these L of P F alpha will be equal to the sum as I runs from 1 to n of the little mi's delta alpha sub I, where the big M sub i's is, of course, the supremum of F over the subintervals created by the partition, and the little m sub i's are the infiniums of f of x over each subinterval created by the partition. And then thirdly, I guess this should have been second, and this should have been third. Fourthly, we have this interval, but I'm going to put a superscript here with a bar of f of x d alpha of x, or just d alpha. Okay, so what is it going to be equal to? It's going to be equal to the infimum over all partitions of the u, p, f alpha Similarly, we have a fifth definition, that is the integral from a to b with this subscript of f d alpha. This is going to be equal to the supremum over all possible partitions of a to b of these lower integrals of p with respect to f and alpha. I shouldn't have said integrals, should have said sums. Okay. So that's what we have. And then sixthly, if from a to b f d alpha with a subscript r is equal to a to b, the integral from a to b of f d alpha, where we have the so superscript is equal to the subscript bars. Then the Riemann-Stieltjes integral of f with respect to alpha over a to b is this integral from a to b of f d alpha, which is going to be equal to the subscript bar from a to b, integral from a to b of f d alpha, which is the same thing as integral from a to b with the superscript bar of f d alpha. And we say if f is Riemann-Stieltjes integral on a to b, okay, with respect to alpha, then we write f is an element of these Riemann-Stieltjes integral functions of alpha. Okay, so this is an extension of the Riemann integral. And here, just as a note, if alpha is equal to x, function x, then the Riemann Stieltjes interval is the Riemann interval. Okay, here's the definition. It says, we say that a partition script P star of A to B is a refinement of the partition script P of A to B if, well, P, script P, is a subset of script P star. Okay. So everything that's in script P is in script P star, but script P star may have more things. Okay. And then, as a definition, given two partitions, say P sub 1 and P sub 2 of the interval from A to B, then we say P star is their common refinement. If P star is equal to P1 union P2. Okay, it's a theorem as follows. If P star is a refinement of P, then L of P, script P of F and alpha is less than or equal to L with the refinement partition F and alpha, and it turns out that U of P star F alpha will be less than or equal to U of P F alpha. Okay. So here, for the proof, I will only show that this lower sum with P PF alpha is less than or equal to the lower sum with the refinement F and alpha. And we'll leave the inequality involving these upper sums to the students. So probably a homework assignment. Okay. Okay. So this P star is a refinement, so it's got more, if you will, more points than P does. And so the simplest case is just got one more point. So here's what we'll say. This would be case one. Suppose P star has just one more point than P. Okay. Let this extra point be noted. The X star. Okay. And suppose we have X sub I minus 1 is less than X star, which is less than X sub I. So X sub I minus 1 and X sub I are part of the original partition P, and this X star is the additional thing that's being thrown into P star. Again, where Xi minus 1 and Xi are two consecutive points in P. Okay. Now, for notation's sake, what we'll say is we put W sub 1 is equal to the infimum of all the f of x, and this is for xi minus 1 less than x less than xi. And W2 equal to the infimum. I made a mistake here. This is X star. And W2 is the infimum of the f of x values for, and here I should have less than or equal to. And here it's X star less than or equal to X less than or equal to Xi. Okay, here's what I'll say. And this is straight from the text. It says clearly W1 is greater than or equal to little m sub I. Okay? And same thing for W2. It's going to be greater than or equal to little m sub I. Okay. What was this m sub I? It was the infimum of f of x values, output values, over the region from x sub I minus 1 up to x sub I. And what we're doing is we're splitting that region into x sub I minus 1 up to x and looking at theta over that. And so the smallest, if you will, over that smaller region is going to be bigger than the smallest over a bigger region. And that's the reason we have these two inequalities. Let me say where the m sub I is equal to the theta of the f of x for, here we have x sub I minus 1 is less than or equal to x is less than or equal to x sub I. Okay, that's what we have. So if we look at these lower sums, that is, if we take the lower sum with the refinement partition, f and alpha, minus the lower sums with the partition of f and alpha, okay, then they're going to be exactly the same most of the time. The only time that they're not the same is really when we're looking at that interval in between x sub I minus 1 up to x sub I. And so in that situation, what you're going to have is w sub 1 of alpha x star minus alpha x sub I minus 1. Yeah, that's the first part. And then plus w sub 2 times, here would be alpha x sub I minus alpha of x sub star. Okay, that's what we have. Minus, the term from here is going to be m sub I times alpha x sub I minus alpha x sub I minus 1. Okay, so that's what we have as the subtraction between these two lower sums. Okay. Okay, if we add and subtract the same things, we get that this is equal to, and expanding things. So we have w, first of all, expand things. It's w alpha x star minus w sub 1, let's just say, alpha x I minus 1 plus w2 times alpha x I minus w2 alpha x star, okay, and then minus m sub I, that little m sub I, alpha x sub I, plus, it will be m sub I, alpha x sub I minus 1. Okay, I'm going to add and subtract the same things. I'm going to say, this is w sub 1, alpha of x star, minus, rearranging them, m sub I times alpha x star minus w sub 1 alpha of x sub I minus 1 plus m sub I times alpha x sub I minus 1 plus W2 times alpha x sub I minus m sub I times alpha x sub I minus W2 alpha x star plus m sub I alpha x star. what I've subtracted and added, I think, is the m sub I times alpha x star, both of these spots. I think they were there before. And so this is going to be equal to, this can be rewritten as W1 minus m sub I times the quantity alpha x star minus alpha of x sub I minus 1, and then plus W sub 2 minus m sub I times the quantity alpha x sub I minus alpha x sub star. Okay, now, because the alphas are increasing and the x sub star was bigger than the x sub I minus 1, this is positive. Likewise, this is positive. We already know that W1 is going to be greater than m sub I, and W2 is going to be greater than or equal to m sub I. So what we have here is a non-negative times a non-negative. That's definitely going to be something greater than or equal to 0. And similarly, this is going to be greater than or equal to 0. So we have that this is going to be greater than or equal to 0. So in this case, we have that this lower sum, P star F and alpha, is greater than or equal to this lower sum, which is P F and alpha. And that's what we want to show, but that's just in this case. If we have the other case where P star contains more than, or contains, let's say, K more points, than P, then we repeat the argument we just gave. K times to get the same result. So to get that the lower sum of the refinement is bigger than or equal to the lower sum of the original partition of F and alpha. And that's the proof.
Ladies and gentlemen, that'll be enough for this lecture, and we'll start with more theorems about Riemann Stieltjes integral next time. Thank you very much.